So today we are going to discuss about colligative properties, and we will be discussing two colligative properties. First is relative lowering in vapor pressure and second is elevation in boiling point. Now first of all, what do we mean by colligative property? Now all such properties which depend upon number of moles of the solute. Okay, in solution there are two things, one is solute and other is solvent. So any property which is dependent on solute only, irrespective of its nature, then that property is called colligative property. Now there are four properties. One is relative lowering in vapor pressure, another is elevation in boiling point, third is depression in freezing point, and fourth is osmosis. In all these properties, the value depends on amount of solute. So these four properties are known as colligative properties. Now what the property is, it is suggestive from the name itself. Now see, in first property, relative lowering in vapor pressure, what is going to happen? The vapor pressure of the solution. Now see, one more thing which you have to remember is, these properties are for that binary solution in which non-volatile solute is added. When we make a solution in which non-volatile solute is added, in that solution we will see these four properties. Okay, so colligative properties are related with the binary solution containing non-volatile solute. Now what does it mean? Vapor pressure of the solution will be low relatively. Relatively means we can relate it with either solute or with we can relate it with solvent. Okay, previously we will take only solvent, then whatever is the vapor pressure, if we add in that non-volatile solute, then the vapor pressure of solution will be low. Okay, that is called relative lowering in vapor pressure. Similarly, boiling point, whatever is the boiling point of pure solvent, that boiling point will increase if we add some non-volatile solute in that. Okay, now let us discuss first one, relative lowering of vapor pressure. Okay, now see, what we know, that vapor pressure of a solvent in a solution is less than the pure solvent. Okay, this we have discussed earlier. Now Reynolds gave one relation. This is the relation given by Reynolds, where P1 is the partial pressure of one component. Now here one component is volatile component. Okay, so it is for solvent. When we are talking about a solution, then it is for solvent, because solvent forms vapor, it is volatile. So P1 is equal to x1 into P1 naught. P1 naught is vapor pressure of the one component in its pure state, and x1 is the mole fraction of the component. Okay, now how much reduction, how much decrease, how much lowering in vapor pressure will be there? That is noted by delta P1. Now delta P1 denotes lowering in vapor pressure. Now delta P1 is equal to pressure of the component in its pure state minus partial pressure in the solution. Okay, so when we will solve it, we will get this. We are getting lowering in vapor pressure is equal to P1 naught and within bracket 1 minus x1. Now we know x1 plus x2 is equal to 1. So it means 1 minus x1 is equal to x2. So what we are getting? We are getting this relation. Delta P1 is equal to x2 times P1 naught. Okay. Now if I take P1 naught to left side, then I will get this delta P1 over P1 naught, and right side what I will get? x2 only. Now if we talk about delta P1, then it is lowering in vapor pressure, and if we talk about delta P1 divided by P1 naught, then it is relative lowering in vapor pressure. Okay, so delta P1 is equal to P1 naught minus P1. Okay, so this is the relation. Now this relation is called relative lowering in vapor pressure. Sometimes we are asked a question, how will you prove that relative lowering in vapor pressure is equal to mole fraction of solute? Now here 1 is a solvent, just like I told here, and 2 is solute. So this much is relative lowering in vapor pressure and this much is mole fraction of solute. Okay, now how can we determine the molecular mass if we know relative lowering in vapor pressure? Okay, now see, just now what we have written, relative lowering in vapor pressure is equal to x2. When we open x2, which is mole fraction of second component, then it will be n2 over n1 plus n2. Okay, now for the sake of simplicity, what we do, we already know that number of moles of solute will be very less as compared to number of moles of solvent. So we can neglect this term. We can write here, in this case, this can be written as n1 plus n2 is approximately equal to n1 only. Okay, why we have done this? Because number of moles of solute are very less as compared to number of moles of solvent. So now when we put the values, n2 is equal to w2 over m2 and n1 is w1 over m1. Okay, so this we will get, and this is the relation which will be used for calculation of molecular mass of solute. M2 is molecular mass of solute. Rest things will be known. This is to be calculated. W2 will be known, M1 will be known, W1 will be known. Either relative lowering in vapor pressure will be known, or we may be given lowering in vapor pressure. So by using this relation, we can calculate the molecular mass of solute. Now see, one question here it is, vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile non-electrolyte solid weighing 0.5 gram when added to 39 gram of benzene having molecular mass 78 gram per mole, vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? Now see, whenever a numerical comes, then we have to read the numerical twice first of all. Then we will come to know what all things are given. Now what is given? Pressure of solvent in its pure state is given, this one. Pressure of solution is given, this much. From the formula itself we know the molecular mass of solvent. Okay, then weight of solute is given, then weight of solvent is given. Now equation 2.28 means just now the equation which we have done. Just now what we did, this relation we have done, this one, this relation. Okay, in this relation all things are given except M2. This is also given, this is also given, this is also given, and this whole thing is also given. So what we do, we put all the values here. Okay, all the values we will be putting here, and we will get the molecular mass value as 170 gram per mole. Okay, now let us come to second property, elevation of boiling point. Now see, when we are talking about boiling point, then from the definition, what is the definition of boiling point? The temperature at which vapor pressure of a liquid becomes equal to atmospheric pressure. So from this definition we have to think about increase of temperature, its relation with boiling point. Okay, now see, what we know till now, vapor pressure of a liquid increases with increase in temperature. Okay, this is known to us. Now water boils at this temperature because at this temperature what happens, according to definition, vapor pressure of water becomes equal to atmospheric pressure. Okay, now we also know that vapor pressure of solvent decreases in the presence of non-volatile solute. This we have done earlier. that when we add some non-volatile solute, then its molecules come on the surface, and so vapor pressure decreases. Okay, now when we are talking about these all things, then if we talk about a solution in which non-volatile solute is added, then what we will see, its vapor pressure value will decrease. It means we have to heat it for long. We have to heat it for long, so that there is increase in vapor pressure, and that vapor pressure becomes equal to atmospheric pressure, and only then the solution will boil. Okay, now see, look at this diagram. This diagram is between vapor pressure and temperature. Okay, now these two lines, this line represents solvent and this line represents solution. Now this line is the pressure where our solvent or solution must reach so that it starts boiling. Okay, now this vapor pressure should be equal to atmospheric pressure, and which is 1 atmospheric. Now when we draw a perpendicular, then for solvent it comes about here, and for solution it comes about here. So this side temperature is increasing. It means the boiling point temperature of solution is higher and boiling point temperature of solvent is lower. Okay, now whatever is the difference between the two, that is termed as elevation in boiling point or elevation of boiling point, because when we are having only solvent, then its boiling point temperature is this much. Now when we have added some non-volatile solute, then its boiling point has increased and it has become this much. So this much is the increase in boiling point. Okay, now mathematical form of this elevation of boiling point property, let T be naught be the boiling point of pure solvent and Tb be the boiling point of solution. Then elevation in boiling point delta Tb is equal to Tb minus Tb naught. Now it is always higher value minus lower value. So Tb is boiling point of solution, which is higher, and Tb naught is boiling point of solvent, which is lower. So whatever is the difference, that is called elevation in boiling point. So it is denoted by delta Tb. Now experimentally it is observed that delta Tb is proportional to molal concentration of the solution or molality. So this will be termed as colligative property. Sometimes we are asked, how will you prove that this is a colligative property? So what we do, we write like this, we draw the diagram, and then we say that experimentally it has been observed that this value, this increase or this elevation of boiling point depends on molal concentration of the solution, and so it is a colligative property. And then what we do, we draw, we write this equation, delta Tb is equal to Kbm. Here sometime we are asked, what is Kb? One mark question comes, that define molal elevation constant or ebullioscopic constant. Now see, in this relation what we can do, if we take molality is equal to 1, then what will happen, delta Tb will be equal to Kb. So from this relation we can define this. What we will say, we will say molal elevation constant is equal to elevation in boiling point for 1 molal solution. Okay, so this way we can define it. Now molality is equal to this much. If we apply the formula, number of moles of the solute dissolved in per kg of the solvent. So if we put this value here, then we will be getting delta Tb is equal to this much. Okay, and from here, because we have to calculate the value of M2, so when we rearrange, then M2 becomes equal to this much. Okay, so here all the values are known to us. Kb has fixed value at fixed temperatures, so this value is given in the questions, and we can calculate the molecular mass of solute. Now see, here there are two examples based on elevation in boiling point. First example is 18 gram of glucose is dissolved in 1 kg of water in a saucepan. At what temperature will water boil at this bar? This bar or 1 atmospheric, 1.013 bar or 1 atmospheric is one and same thing. Kb value is given 0.52 Kelvin kg per mole. Okay, now first of all what we will do, we will calculate the number of moles of glucose. From the formula we will come to know the molecular mass of glucose, and then number of moles of glucose will be 0.1 mole. Now in kg we have to convert our solvent, so it is already given as 1 kg. Now we have to calculate molality. Molality is number of moles over weight of solvent in kg, so it comes out to be 0.1 mole per kg. Now we will apply this formula and we will get this value. Okay, now what we got till now, we got elevation in boiling point. Now it depends on what is asked from us. Okay, what is asked? At what temperature water will boil? Okay, so we have to calculate the boiling point temperature of solution. Okay, so boiling point temperature of solution is equal to boiling point of pure solvent plus elevation in boiling point. So it comes out to be this much. Okay, so this is to be remembered. Two relations we will be dealing with, delta TB is equal to kbm, and another one is delta TB is equal to elevation in boiling point, means boiling point of solution is higher, so delta TB is equal to TB minus TB naught. So these two relations we will be using for solving the numericals. Now let us come to second one. The boiling point of benzene is given when 1.80 gram of non-volatile solute was dissolved in 90 gram of benzene. The boiling point is raised to this. So raised to this means now boiling points of solution is given, not elevation is given. Okay, so this is boiling point of solvent, this is boiling point of solution. Okay, this is weight of solute and this is weight of solvent. Kb value is also given. Now we will put this in the value in the equation which we calculated just now. We calculated this relation. See, this is the relation which we calculated, this one. Here W2 value, Kb value, W1 value and delta TB value, these are to be put, and then we will come to know the value of M2. Okay, now see, first of all we have to calculate delta TB. So delta TB is equal to this much. Okay, this is delta TB. No, this is not delta TB, this is Kb value. Kb value, this one is weight of solute, this is 1000 multiple, and this is elevation and boiling point, and this is weight of solvent. When we will put all the values, then we will calculate we will come to know what is the molecular mass of solute. So two properties only we have discussed till now. Rest of the two properties we will discuss in next session. On the basis of this, you have to solve these two numericals and this theoretical question. Okay, thank you.